Yeah, hello. Thank you for the introduction. As Christian mentioned already, a bit less technical presentation, but important topic for the fuel cells, because fuel cells do not work alone. They need the hydrogen, and the hydrogen needs to come from somewhere. So it's about integration of fuel cells and electrolysers in the power grid applications. Some words about our company, Powercell in Sweden. We are a small company, recently with extreme growth. So we are increasing from 30 to over 100 people within 2.5 years. So it's an interesting journey. We are working on fields of fuel cell systems, fuel cell stacks and systems for marine, stationary, off-road and aviation. Aviation is a surprise for us as well, actually. You may miss the on-road on this slide, but this is simply due to the fact that we have a licensing agreement with Bosch. So Bosch is using our stacks and is supporting the on-road market. Today we focus a bit, I want to focus on our stationary portfolio. We have systems from the range of 5 to 200 kilowatts. The main seller, I would say, is our PS100 system in the range of 100 kilowatt. And the PS200 system is the interesting system for bigger installations, because we also can scale this up and connect in series so that we can range up to megawatt solutions with these systems. We are also working on containerized solutions where we try to package the complete equipment so that it's more or less plugging in the hydrogen and getting out the power on the other side. Also here in a range from 5 to 15 kilowatt with our VS5 systems, over to 100 and 200 kilowatt systems in single container solutions, but also then for megawatt installations in connecting different containers. So what about power integration? What does this mean? This means somehow we produce renewable energy somewhere, and we need to transfer this through the grid, but the grid does not always have the capability to take up all the energy. So we need to find a solution to save this energy for later when it's really used. And the common way for this to do is with electrolysers or with batteries, of course. On the other hand, sometimes also the grid is not, the renewable energies are not available, so we need to put in the power from somewhere else, and then we reuse simply the energy that we stored in a fuel cell solution and put it back into the grid. Or even as is sketched here, the hydrogen can also be used, of course, for mobile applications, running the fuel cells in the truck, or using it directly into building infrastructure, as both as a supply power, but also as a backup power solution, of course. And we see these 5 fields basically as interesting: power supply and regulation, grid stabilization, peak shaving, and off-grid applications, and of course also the backup power solutions. I would like to show you one customer case where we did some work. This was about of a 2.5 gigawatt peak solar plant in Southeast Europe. So the total calculated energy output was about 3.75 gigawatt hours per year. And there was a request that this plant should be capable to extend it with a electrolyzer fuel cell solution to be able to supply 2 megawatts for 1,500 hours per year, which means around 4 hours per day, and together with a maximum continuous power supply request of 2 megawatts for maximum 8 hours a day. So, and then the questions came, okay, what does this mean for the fuel cell capacity? And what electrolyzer do we need? And what about the storage? In the end, my colleague Jan from sales came to me and said, is this feasible? And I'm very happy that he asked this question, actually, because this triggered something in our company. And we started to think about integrating our fuel cell into the grid. And look how this works out. And happily, there was some pre-work done by GT, which made the startup bit easier for us. So we had this model from the blog, from Joe and Holden Simons, and we modified it. So we took out the batteries, we took out the wind, we added an electrolyzer, and we added a fuel cell, and we implemented a new control strategy. Somewhat about the battery, we know that we need a battery, and we had it in the beginning. But we recognized also that when we do our simulations, we are running on an hourly basis, and as we don't see the battery as a storage device, but more as a bridging device between the lack of solar power and the power that the electrolyzer needs, or that the fuel cell could supply, that we are below this 1 hour, and we simply dropped it off to get a bit more simplification. The input data for the solar power plant comes from a databases, which was a EU-funded project, PVGIS. Very interesting. I can recommend it for you if you are interested in solar power. Then you can calculate it on your own and can check if your suppliers are telling you the truth. They work quite well. The required input is the location, the installed peak power, an estimate of system losses, which is, as a standard, defined as 14%, and the type of the installation. So is it a fixed installation? It's on the roof? Is it on a free field? And so on. So you can parameterize all this and put it into this interface. You can choose between different databases. It's really, really good tool. So sometimes EU funding leads to something that is really useful. What comes out of this is a profile for the solar energy that you can get, and you get it on an hourly basis. So you can download the file and implement it as a source into your models, which in the end looks like this. It's a bit messy, but you can see that we have phases where the solar energy is, of course, very low. Then it's very dense in the middle, and during autumn and winter, it's of course low again, even in Eastern Europe, so which is normally a bit warmer than Sweden, but also they have some lack of sun in the winter. As a next step, I added in this plot the times when we have so much energy that we can run our electrolyzer. So this means in all these areas where the green is, we have so much sun power left that the electrolyzer can be driven directly from the sun, from the solar power. Now the blue ones, to achieve this 2 megawatt for 8 hours per day, between 7 and 15. This was the boundary that we put in. It's still quite a huge need from the fuel cell system to supply this power. Yeah, and you can easily imagine that if you want to run this fuel cell system that much, that needs also a lot of hydrogen. And it's simply not feasible to produce the hydrogen alone with the solar energy. We more or less need to run the electrolyzer also during night from 9 o'clock in the evening until 6 o'clock in the morning, which we have assumed in this case to be the time when the energy is cheap. The electrical energy is cheap, but we need to run it every day more or less throughout the year. Yeah, which of course also results in a quite huge amount of hydrogen that will be produced, but also needs to be stored. So we end up in a storage of about 33,000 kilograms of hydrogen on site, and this is of course driving the costs. And you also see here that even the hydrogen that we produce is not sufficient enough to supply for this use case. Yeah, this is basically no big surprise, because we see also that this rule violates the rule number 1. So when we calculate the 2 megawatt for 8 hours, then we are running on 3,000 hours per year, but we have an estimate that gives us 1,500 hours, which results more in a way of 4 hours per day. So we try to come closer to to this proposal. Try to scale down the supply a bit and said, okay, what happens if we have 2 megawatt for 8 hours, but only in 3 days per week, which is then about 1,200 hours and comes closer to what we have started with. And here it looks a bit better. Number one, we managed to produce all the hydrogen that we really need. Number two, we need to run much less. We have much less operation of the electrolyzer on nighttime. So it's basically in the autumn and in the winter when this is needed. And we come a bit down in the storage size. So from 32,000 to 20,000 kilograms. So this means at least a bit improvement on the storage side. The drawback on this is that we have solar energy that is actually not used. So what should we do with it? It can produce more hydrogen and try to sell it, or you can try to get a better contract for your electricity supply and have an ability to get it off, or simply disconnect from the grid. So better, but not good, I would say, because the storage is still a problem. So we tried another scenario. We said, okay, we reduce the supply to 1 megawatt only for 8 hours a day, 7 days a week. And we limit the storage. We go to 5,000 kilogram storage only. So we have a limit of what we can store. In the beginning, the storage is almost empty, not completely empty, just to improve the startup here. We have to operate the electrolyzer during night, but we can keep this minimum level in this time and supply. And then during summer, in the spring, which has been identified as a very good time to produce hydrogen because the sun is really good here. The efficiency of the system is good. We fill up our storage. And during summer, you see, we are more or less able to keep the storage level. And some in the times where we have a dip, then we start the electrolyzer again and try to get this 5,000 kilos filled up. But then from week 40 and onwards, it's going down, and we reach this minimum level again, and then we need to start up the electrolyzer to keep the level that enables us to supply for the next week, the next 3 days. And what we see is here that, okay, 5,000 kilowatt storage seems to be a good size. The electrolyzer in the 2 megawatt range is not cheap, but okay. We have a hydrogen balance and we have minimized the night operation, but the drawback is that we have quite high unused solar energy. Yeah? So this is the black curve here, tells you the story. We cannot utilize the sun when it's shining during summer. Yeah? So this is the drawback. Short summary of all this. So this Powergrid modeling, this helps us a lot, and also our customers, to understand the situation. This is not that obvious, and there's still a need. We get, honestly, we get quite silly requests. Yeah? So because everyone has high expectations, but they are not realistic. Yeah? And the same for us. For us, it's always difficult also to understand the customer side. So this type of models, now on the stationary, but also in different applications, helps us a lot to get a better understanding of what the customer really needs. And it's both, it's learning and teaching. And of course, this helps us also to do analysis of different potential scenarios, and to, by that, biasing a bit the expectations and the possibilities, which makes in the end both a bit more happier, the customers as well as the supplier. And what are the learnings so far? One thing is clear, on-site hydrogen storage is a challenge. So if if this really should happen, then we need to have a vital hydrogen market. This is the simple answer. We need to have consumers and producers and a possibility to buy and sell hydrogen on a more regular pattern. So if we need to store or on site and everyone needs to do it on his own, this will not help us and will keep the costs on a too high level. We also see that there is hardly any standard use case. So you cannot say, okay, you have the one solution fits all. It's always a development. It's always a need for adaptation in both in sizing, in the way what you can supply, depending on the circumstances, depending on the sources that you put in, depending on the use case. The other thing is also that it's no easy way to evaluate the result. Of course, you can always take the costs, but when we use the costs, then we also need to keep in mind what I wrote in the next row, though, that electricity prices and available energy is always history. It's always data that we have from the past, but it doesn't tell us something about the future. Is really the energy in the future at night so cheap as it is today? When we have solar power plants, they produce the energy at daytime. So maybe this will shift. And honestly, no one of us has the answer now. I tried to do something, and I tried to calculate the efficiency of power to gas and gas to power transfer by only considering the extra energy that I need to buy from the grid, which turned out in these scenarios, when you see this from the first scenario, which was really unrealistic, you see this already here. Then this is the electricity consumption of the electrolysers, whereas this is the electricity that we produce that we provide by our fuel cells. Yeah, so you see that the gap is simply too big, and this results in a rather poor efficiency. Yeah, so we are in the range over the year. Still at 30%. So, but I think we all know that we need to be better. So when we look into the other two use cases, then we see that we get them much closer together, and especially the last one here, I would say is really a good balance and something that could make sense. And if you calculate this into an average efficiency, then we are in the range of 50% for the 3-day case and around 60% for the 1 megawatt case. So I think this is something that is closer to what we really can call as a offer. Yeah. Next steps for us is of course model improvements. So right now it's really a very simple approach. We would like to implement a more detailed storage model, for example. We want to implement, from our side, degradation models to understand this and to really can calculate this. We want to implement better and more realistic control strategies for the whole plant and simply controlling after the time. And of course also add more physics. So right now everything is table-based, so you don't need GTC to do this, but for us it's a good thing to have this in a common environment, and then we can simply add the complexity where we need it and keep the simple models where we don't have better ideas or where we simply don't see a need for more detailed modeling. And what is also an interesting question is to get in statistical models, as we know that we have variations in the production and in the supply of renewable fuels. So would also be good to have a kind of a variance of this data. We also want to further utilize this for further topics like waste heat utilization. So we produce heat from our electrolysers and the fuel cells. How to integrate this into the model? Also optimization for specific customer use cases with better definition of goals, and also from a business perspective to understand the business models. How does it look for leasing agreements, maintenance, and things like that? Yeah. And yeah, finally trying to get this to a level of a digital twin, which helps us then when we have implemented these strategies also to be able to have models telling us if it's time for maintenance or service or something like this. Some thank you to my students. Alice, she did a great work. She's now finished. Stefano, working as an internship student for me right now, and also my colleague Jan for reaching out, actually. So this, you don't meet these people so often as an engineer, yeah? And also to our partners, Euromechanique. They are experts on hydrogen infrastructures and also redistributed for the HTEC electrolysers in Sweden. Yeah, and if you are interested in collaborating, I mean, this is a network, yeah, then please contact me. I'm open to share information and to share basic models. And then if you have an electrolyzer model that you think is good, then tell me, okay, hey, then I'm happy to get this. And if you say, okay, I have an idea, but I don't have a clue about fuel cells, then let me know. Then I can maybe provide you somehow a fuel cell model that will help you. Yeah. Thank you for your attention.
Yeah. Thank you, Stefan, for the very interesting and different topic from others, but I think it's very important to just keep an eye on the potential applications. And so are there any questions from the audience right now? If not, then maybe I have a quick one. So have you considered, especially to help your sales colleagues to implement this as a GT Play model so that it's really possible for users to access it from the web so they don't need to ask you to run the model?
Yes, we have discussed this. I think it was for us a step too early, maybe for you as well. But this is definitely also a future topic that I simply get rid of this work, yeah, so that my colleague Jan can do it with itself.